So looking at the calendar, we've done 3 days on antiderivatives. Friday, Monday, Wednesday. We took the quiz on Wednesday. Today we'll do Riemann sums, and tomorrow we'll make the connection between Riemann sums and integrals. So those are kind of the 3 topics for the test. Just plain antiderivatives, plain Riemann sums, and then this connection between the 2 of them. So I guess even before we start talking about Riemann sums, let's keep talking big picture here. The 4th through the 9th was all antiderivatives, sort of culminating in the quiz that you took yesterday. Power rule, trig rules, exponent rule. Because there is no chain rule, there is no product rule or quotient rule. So in some sense they're easier. I don't know if that's accurate or not, but on today we're going to talk about Riemann sums, which are area, or which is an area, and actually it's an area estimation. And so you're rightly, hopefully, concerned or wondering, like, how does an antiderivative relate to area? That doesn't seem like it flows. Like, usually math is pretty easy to see the connection from one day to the next. This is not one of those days. Like, we're going to be area estimating, and that doesn't feel like it has anything to do with antiderivatives until we get to tomorrow, and then we'll learn. Actually, we may see the edge of it today, that an antiderivative actually equals the area, which is, I don't know, weird. Yes. It's maybe not a wow moment for you, but it was a wow moment when they figured this out. You could figure out the area under a curve by doing an antiderivative of it. It is a bit of a wow moment. Okay, but before we get there, we got to talk about finding the area under the curve, not with calculus, but with like basic geometry and area formulas. And so there's lots of formulas that some books go into on this lesson, but we're not going to do the formulas. The only formulas we're going to do is the area of a rectangle is base times height. If you can remember that, then all we're going to do is add up areas of rectangles. All right, so we'd like to be able to find the area under a curve from A to B. So you got 4 graphs down there, same graph, all from A to B. Riemann sum approximations use rectangles to approximate the area under the curve. And we use rectangles because we know how to find the area of a rectangle very easily. So the math, at least some of the math, is easy because the area of a rectangle is easy. Riemann sums are named after this German guy, Bernhard Riemann, 1826 to 1866. That's a short life for Bernhard. I don't know the events surrounding his death.
Then again, it was the 1800s.
That's right. It could have been, who knows. So anyway, let's draw rectangles using the left side of each rectangle as the height of the rectangle. So let's back up a little bit. Let's make 6 subintervals first. 6, I just picked 6 because I think that's a nice, easy number to deal with, and because it's not too hard to divide the width in half, and then to divide it in thirds. You can see my pencil marks there from when I was seeing if I could do this by hand. Relatively easy. So 6, roughly equally partitioned subintervals. And if we want a left sum, then that means we'll take the height of a rectangle from the left. So there's one rectangle. We come from the left. 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 And come from the left. So there's my left-hand rectangles. Because each rectangle comes from the left side of the interval. And so you could think, well, is that an overestimate or an underestimate, or is it probably good? Who knows? It's probably under, because this one's under, that one's over, but then both of those are under pretty big time, so it's probably an underestimate. But it's a left-hand estimate. Let's do a right-hand estimate. So again, divide it into 6 equal subintervals. As equal as you can get them just by sight for now. And now we're going to come from the right. So I think it's helpful to start all the way on the right-hand side of the overall interval. Start all the way over here. And so your first height, your first rectangle would be that one, because you're coming from the right. Then your next rectangle would be coming from the right there. And then your next one. And there's your right rectangles, because you're using the heights at the right side of the intervals. Does that make sense? Like the names are supposed to make sense. Come from the left for a left Riemann, come from the right for a right Riemann. We can also do a midpoint sum. Let's again use 6 subintervals. So again, cut it in half and then cut it in thirds. We got our 6 petitions up, or I guess it's 5 petitions to make 6 partitions, to make 6 intervals. So where do you think we want to draw the height at if we want to use a midpoint sum? Pardon? They draw rectangles at the midpoint of each width. So instead of doing the left or the right, we're going to use the middle. So wherever the middle is, that becomes our height of that rectangle. Midpoint sum. Thank you. And you might think that the midpoint is more accurate, especially on this one over here, because it looks like those two would offset each other. Those two would kind of offset each other, so who knows, the midpoint might be more accurate. But there's a better way to get a more accurate result. We'll talk about that in a minute. Area of a rectangle is base times height. So for those 3, that's the trapezoid. For those 3 methods, just boxed in all 3 of those, all you do is base times height and add the rectangles. Again, that's where it can lead to some crazy. If you try to simplify and get a formula, you can, but it's not worth it. It's just base times height plus base times height plus base times height, however many times you need to. The last option is to do a trapezoidal sum. Again, let's use 6 subintervals, just so our pictures will all look the same. So cut it in half and then cut it in thirds to get the 6 intervals. And this one's kind of hard to draw because the trapezoids are going to be pretty close to the actual curve. So we find the area of the trapezoids. It says So it tracks the curve pretty well. So a trapezoidal sum is usually pretty accurate. Area of a trapezoid, you might not remember, but it's related to the area of a rectangle. Instead of base times height, it's the average of the heights. So h1 plus h2 over 2 times the base. And this is another one that leads to all sorts of formulas, but don't memorize the formulas. Know how to find the area of a trapezoid. You do need to know that formula. And then you just go piece by piece and add them up. What's that? Yeah. So this is the part that's really easy. When we get there, like all we're going to do is base times height plus base times height plus base times height, however many times we need to. All right, the area of each rectangle is base times height. The base is the width of the subinterval. Zoom in a little bit. The base is the width of the subinterval. We call it delta x, that change in x. How wide is the subinterval? And the height would be the height at the left or the right or the midpoint, depending on which one it asks for. And it will specify. It'll say find a left Riemann sum for this data, or find a right Riemann sum for this function. Each height is the function value at each x value. Come back over here to this previous page. So this height right there, that height is f of a. Right? That height is f of a. Each width is delta x. And so you're doing a y value times a delta x, a y value times a delta x, a y value times a delta x, all the way down. The area of the sum of all the areas, the area is the sum of all the areas of the rectangle. Just add them up. Like, that sounds fancy. Add up the rectangles. Like, that's the main point of the whole lesson right there. You got lots of fancy stuff going on. All you're doing is adding up rectangles. Maybe adding up trapezoids. Now, what gets a little bit strange, this will start to make the connection till tomorrow. So you can kind of ignore all of this stuff. See if I can simplify this a little bit. So that summation formula, the summation sign, you remember that from pre-cal? Sort of. It means add them all up. It's a sigma. Add up all the areas. That's what we would do to get the answer. Add up area 1 plus area 2 plus area 3, all 6 areas. But if we want to get a little bit fancier, the area of a rectangle is base times height, or height times base. The height is f of x, and the base is dx. So we're adding up a whole bunch of y values times delta x's. Here's where the jump comes and where we just lose people. So how could we make our approximation a better approximation, right? Right now this is an estimate, and maybe it's good, maybe it's not so good. But what could we do that would make our estimate more closely match the actual area under the curve? use more subintervals. Yeah, make delta x smaller and squeeze 100 rectangles in there. Like, you wouldn't want to do that by hand. Like, you could write a computer program to do that. But that would get you pretty accurate, right? If you had 100 little subintervals in there, you'd have a pretty accurate estimate. If you wanted a completely accurate, more rectangles leads to more accuracy. And then here's where things get a little bit crazy and why we use calculus. If we had infinite rectangles, it's like, well, how would you draw that? Because that would take a while. But if you could do infinite rectangles, then you would have the exact area. Right? It wouldn't be an estimate anymore if you could somehow squeeze all of the rectangles in there. So if you went from 1 to infinity, f of x, and now instead of delta x, because delta x is a finite distance, but if we shrink delta x down small enough and make it like a very, very small, we change it to dx. And this is a sigma, and another letter for sigma, or another way to write sigma, is that this antiderivative sign is an elongated s, which means sum. So if you thought that looks like an s, you're right. That's where it comes from. So we would sum all of the heights dx, and so our area is an antiderivative. That's dipping our toes into tomorrow. Today we're not going to do infinite rectangles. We're just going to do 4 or 5 or 6 rectangles and add them up. All right. Again, this hard stuff is a taste of tomorrow. Let's do some example problems, and I think you'll see that this isn't as hard as it seems to be. Tomorrow is a different story, but today, pretty straightforward. Let f of x be a continuous function. Selected values of f of x are given in the table above. So we don't have f of x, but we've got a table with some of their values. Estimate, using a left Riemann sum, and 5 subintervals as designated in the table. 5 subintervals means we'll use 5 rectangles. So 0 to 140, f of x dx approximately equals, because I'm not going to add up the infinite rectangles. That would be tricky to do. Plus, I don't even have all the information to do that. But I can add up 5 rectangles. So let's see, one rectangle would go from 0 to 20. One would go from 20 to 50. One would go from 50 to 70, 70 to 100, and then 100 to 140. So let's add up each of those rectangles, but I need to use the left-hand heights. You use the left heights. So which height, or which one of these numbers is the height coming from the left for my first rectangle? The 100. So the 100 is the left-hand height. How wide is that rectangle? 20. I don't just use the 0. The width of the rectangle is 0 to 20. So there's my first rectangle. My second rectangle goes from 20 to 50. If I want to use the left-hand height, it kind of maybe helps to ignore all the other stuff. Which one of those numbers is the left-hand height? 90. And trick question. Which one of those numbers is the width of that rectangle?
None.
Right. What is the width of the rectangle?
30.
30, because you're going from 20 to 50. Then we look at 50 to 70. Which one of those is the height of the rectangle? 80. And how wide is that rectangle? 20. And then from 70 to 100, what's the height of that rectangle? 80 again. And its width is 30. Then my last rectangle, the height is 100 and the width is 40. Absolutely, that's a safe stop.
Who wants to do that?
Who wants to do all that? I mean, it wouldn't be hard, but who wants to bother with that? Did I mess something up? Yep. I grabbed the left-hand x value instead of the left-hand y value. Yes. So definitely safe stop that. Also, don't go the other way where you don't show that and you just kind of do it in your head or in your calculator because you're like, oh, that's not hard. That's 100 times 20 plus 90 times 30, and you just type it all in your calculator and put the answer down. That won't be good enough because they don't know where that came from. So the grader must see, the grader needs to see all of that stuff. So don't shortcut it so much that you jump straight to the answer because they don't know where that came from. Make sure you show it. And they don't need to see the final answer. All right, estimate using a right Riemann sum. So we use the right values. Okay, so same intervals, but now you're going to use the right values. I'm going to press pause and let you see if you can complete this one. So I came from the right hand side. First right rectangle was height of 130, width of 40. Height of 90, width of 30, height of 80, width of 20, height of 80, width of 30, height of 90, width of 20. Part C. Use a trapezoid sum and 5 subintervals as designated in the table. Okay, so I'm going to have to do a trapezoid, which is the average height times the base. Average height times the base. In some ways, trapezoids are easier because you don't have to worry about left versus right. Just use both of them. Zoom out and get it all on one page here, or all on one screen. So my first trapezoid, my average height is 100 plus 90 over 2. And again, probably best to just leave it alone. Like don't even try to do the math. Sure, the average of 190 is easy, but just write it out. And that width, that base would be 20. Second trapezoid, average height is 90 plus 80 over 2. With a width of 30. Average height, I don't know that you need to put 80 plus 80 over 2, but if you want to make it look like you were doing a trapezoid, that width is 20. And then 80 plus 90 over 2, width of 30. And 90 plus 130 over 2, width of 40. And again, leave it alone. A multiple choice, sure, you'd have to multiply it out and you get an answer, but safe stop that. Part D. Given that f double prime is greater than 0,
So it's
What does that mean? Concave up. So it looks like that.
F prime is increasing.
That would mean f prime is increasing. Given that it's concave up, the approximation found in C, that would be the trapezoids, is that an overestimate or an underestimate?
Over?
Why do you say over?
Because I don't exactly know why, but that just is what feels right in my head.
Well, you're right.
Because it's concave up, and we're like tracing from rectangle to rectangle.
What would you say the trapezoids are? How to phrase it? So definitely an overestimate. All trapezoids are above the curve. Because it's concave up. That's one of those things that you could memorize all these possible combinations, but the better way is to just graph it, sketch it, and see what you think. Number 2. We'll go a little faster here, although this one's a midpoint. I hadn't done a midpoint. Maybe we won't go faster. Let h be a continuous function selected values of h are given in the table above. We want the integral from 30 to 90 using a midpoint sum with 3 subintervals. 3 subintervals. So that means I need to draw my interval from 30 to 50, 50 to 70, 70 to 90 to get 3 subintervals.
Fine.
In some ways it's easier because it's only 3 rectangles.
It's not going to be as exact.
So it probably won't be as accurate, but without knowing the actual function, who knows? You might luck into getting it exactly right. So you don't know. So my first midpoint rectangle, midpoint heights. So my first rectangle, I got more data to look at. Which one of those numbers is the height at the midpoint?
40. Oh, wait. 7.
Careful, I heard 40 and 7. Which one's the height at the midpoint? So, yeah, 47 is the midpoint, but 7 is the height at the midpoint. That's how tall it is. How wide is that base? 20, because the base goes all the way from 30 to 50. And from 50 to 70, a lot of numbers to look at, but 15 is the height, times the base of 20 again. And then 70 to 90,
16 times 20.
16 times 20.
Stop.
And again, safe stop, leave it alone, be done. And without any other information, there's no way to know if that's an overestimate or an underestimate. All right, number 3. Approximate the integral from 0 to 2 of all of that using a left Riemann sum, 4 subintervals. Okay, so from 0 to 2. And I want 4 subintervals. One way to do this is to sort of construct your own. You know, if you like the information in the table, you can kind of build your own table here. So I want to go from 0 to 2. I want 4 subintervals. So how wide does each subinterval need to be? Well, the total width is 2, and I want 4 of them. So 1/2 or 0.5. So let's build our own table. Actually, we won't even have to fill in all of the blanks. Do you know which blank we'll be able to leave blank?
0. Well,
If I'm going to do a left Riemann sum,
you don't have to worry about here.
I'm coming from the left, so I will need the height at 0.
2.
I won't need the height at 2. I can fill it in, but I'm not going to need it because all my heights will be the left-hand heights. So let's find f of 0. That's an easy one. F of 1/2 is going to be kind of a pain. -1/8 plus 2 times 1/4 is a half plus 1. You could leave that and safe stop that and just carry that all the way through. But I think rather than write it all out, I think I can figure out what it is. If I put them all over 8, it isn't too bad. -1 plus 4/8 plus 8/8 would be 11/8. Again, you could leave it as -1/8 plus 1/2 plus 1. It's just every time you needed that, you'd have to write that whole thing every time.
Or you could indicate it as like A or something.
You could make my life hard, and some of you like doing this. You could say equals A, and then put A there, and then use A the rest of the time. Yep. If you go that route, please be exceptionally neat so I can follow your work.
Or at least draw arrows.
All right, plugging in 1's easy. That gets us 2. F of 1.5.
It's the same thing as 3/2.
Yeah, maybe we should think of that as 3/2. So that would be -27/8 plus 2 times 9/4 plus 1 equals B. Do you want me to do that? To demonstrate what to do if you want to go that route? Now I'm feeling lazy. But I'm demonstrating this is perfectly okay to do this because you told me what B is. Now I'm going to use B. All right, so the point of this was to build left rectangles. So the area is approximately equal to. So my first rectangle, what number am I using for the height? I'm coming from the left. 1. And my width, 0.5, plus my next rectangle, 11/8 is my height, and my width is 0.5. We made these to be equal. The subintervals are all 0.5. That makes it a little bit easier. But you do have to pay attention because that's not always the case. All right, the next one, height. No, careful. Maybe unless you're ahead of me. The next one, the height is 2.
Yeah.
And the width is 0.5 because the width is always 0.5 for this one. And then the last one, height is B. Completely okay because there's what B is.
Would you like it if we wrote it in a different color on our tests?
Nope. And it's fine. And, you know, I'm joking about doing this, but if you do that, how likely are you to make an algebra mistake in there? Like none. We didn't do any algebra. We just said, there it is. Called it B, used the B. I don't have to worry about common denominators and all that stuff. We just leave it alone. And that is okay. Obviously, on multiple choice, we're going to clean it all up, so you'll have to be able to do it. But this would probably be one that's a free response, so that we could see that you used 4. You know, you had the 4 rectangles, you had all the heights right, that kind of thing. Just FYI, this area is 3.25, and the actual area is 3.333. So that's pretty close, with only 4 subintervals. If this was super important and we needed a more accurate answer, then maybe we build 20 subintervals or figure out how to get Excel to do 100 subintervals or whatever.
Computers, yay.
Number 4. The amount of water draining in a tank is given by a strictly decreasing. Strictly decreasing doesn't quite mean always decreasing, but it's pretty darn close to always. Meaning it could level off. And so would you say that that's always decreasing? It definitely means it's never increasing. Strictly decreasing, it's never increasing. That'll come up, we'll need that in a moment. Use a right Riemann sum with 4 subintervals to approximate this thing. So I don't even know what all this represents, but I do know how to use a right Riemann sum to approximate that. So WT, that's the height, but I want the right height. Right meaning correct, but right meaning from the right. So we will approximate it with the right-hand heights. And you guys said, sort of voted, that you wanted to come from the right. And I'm fine with that. So I'll look at my rightmost rectangle, and what height will I use out of that rectangle? 43.2. And how wide is that rectangle? 15. My next rectangle, 60.8 is the height, is the right height. And how wide is it? 10. So be careful. That one's, they don't have equal subintervals, but that's fine. Next rectangle, the right height is 71.1, and the width is 5. And then the last one, the height is 78, and the width is 10. Safe stop. No, I look in the notes I'm copying off of. They didn't even do 15 here. They just did 40 minus 25. So really being safe. I mean, they're safe, and then there's like overkill. Like, come on, I know what 25 minus 15 is. But if you were having to do decimals or weird numbers, then don't do it. Safe stop it. All right, is your answer to part A an overestimate or an underestimate to the actual value? Okay, well, it was strictly decreasing. So if I draw a sketch from 0 to 40, it doesn't even have to be very accurate. I'm going to go from 94 down to 43, and it's got to be decreasing the whole way. And I do right sums, right rectangles. I don't even know how many I had. It doesn't matter. If I'm coming from the right, all my rectangles are below, so it's an underestimate. And the reason is all, we should specify, all right rectangles are below the curve. And this is a spot where some textbooks, I think even some teachers, can make these big tables of, okay, if it's strictly decreasing and it's a right estimate, then it's below. If it's strictly
decreasing,
and you can switch them all up, but like, I don't want to remember all that stuff. Just draw a picture. If it's decreasing, draw decreasing, which means coming from the right, you're below. If we were coming from the left, we'd be above. So, draw the pictures. The assignment is the next worksheet, and it really is just adding up rectangles. Adding up rectangles. Adding up rectangles. I do want you to see, so get to number 10 on the next worksheet. It's all under and over estimate. And the only hint I would say is draw pictures. Like, draw what it says, and then you'll be able to answer the question. So on part A of number 10, f of x is strictly decreasing. So we're going down. A left Riemann sum. So if we draw some rectangles or draw some partitions, and we come from the left, what kind of area are we going to get? An overestimate. So without drawing, I think they're hard. With drawing, I think they're easy. So draw what it says, and then I think it makes the question easy to answer. And you can see there's a whole bunch of them there. So the challenge is, can you draw it correctly? Do we need to skip down and do one of the ones that look like it would be hard? Like, I don't know, G. Let's look at G. Given that f prime is greater than 0, what does that mean?
That f is prime is positive and f is increasing.
F double prime is less than 0.
Concave down.
So f is concave down. So I need to draw something that's increasing but concave down. So increasing but concave down. So something like that. Then I want to do a midpoint rectangle. Oh, this one's going to be tricky, I think. You think that's slightly over or slightly under?
Both.
You kind of got to go piece by piece.
Because for each one, the little corner is above the corner.
So you have to compare those corners. This corner is sort of bowed out. This corner is bowed in. So I think there's more area here than here.
Yeah.
There's more area here than here. There's more area here than here.
Doesn't that just depend on how much you draw your line?
Well, if they're asking this question, I think the answer is there's going to be an answer. And so if there's more area that we're missing, then this is an underestimate. That's a tricky one. And it might have been helpful to draw a more extreme version of that. I don't know how to, if you drew it more extreme, would it be more obvious? It might be more obvious. Yeah, if you estimated that with one rectangle, there we go. That would definitely be an underestimate. So maybe the hint is to try to draw it, but draw it extreme, in the extreme, and then you can tell a little bit easier. All right, so we'll answer some more of those, and then tomorrow we'll sort of connect the dots between antiderivatives and area.